Welcome back, everyone. In this video, we're going to continue learning from Chapter 12 of the ebook, looking at gases and looking specifically at what pressure is and the relationships between pressure, temperature, volume of gas, and the number of moles. So what is pressure? We've already discussed that pressure is the force that's caused by molecules striking a surface. And we define that as the force per unit area. The force is measured in newtons, and the area is measured in meters squared. So the International System Unit, or the SI unit for pressure, is the Pascal. And that's equivalent to 1 Newton per meter squared. When we think about pressure and the environment, pressure in the actual atmosphere, you can imagine having a vertical column of air that's a meter by 1 meter in terms of its area, and that it reaches all the way up to the top of the atmosphere. If you were to weigh the air that was in that meter squared column, that would weigh about 10 to the 4 kilograms. So if you imagine the acceleration due to gravity on that on those gas particles within that column of air, that's pulling down those gas particles onto the earth and exerting a pressure on it. That pressure we call 1 atmosphere. And there are a lot of different units that we can use to describe the atmospheric pressure. We use the units atmospheres. We can use pascals. There are units of bar, pounds per square inch, torr, and millimeters of mercury. And there are historical reasons for why there are so many different units of pressure, depending on the application of which field is using pressure in its measurements and its calculations. That they started using different units that made most sense to the situations that they were in. And while at sea level, the pressure is approximately 1 atmosphere. Actual atmospheric pressure is going to vary both with the altitude and with the weather. And it's fairly easy to understand why altitude will play a difference. So again, imagine that we're talking about this column of air that's extending from the surface of the earth all the way to the edge of the atmosphere. If we've all of a sudden increased our altitude, then we've cut off the gas particles that are beneath us in terms of the pressure that they're exerting at that elevation. So if we go up halfway between the surface of the earth and the edge of the atmosphere, we would expect to have approximately 1/2 of an atmosphere. When we talk about gases, we can describe the state of a gas in terms of the number of molecules of the gas, or the number of moles rather, the pressure of that gas, the volume that that gas occupies, and then the temperature of that gas. And that's measured in absolute temperature, units of Kelvin. And 1 degree Kelvin is the same as 1 degree Celsius, but we've added on 273.15. We'll talk about where that number comes from a little bit later in this video. We can measure how these variables depend on each other. There are 4 fundamental relationships that over the years have helped us to understand the behavior of gas particles. They are Boyle's law, Avogadro's law, Charles' law, and the Gay-Lussac law. Let's talk about Boyle's law. With Boyle's law, what we're doing is we're looking at how pressure and volume are related for a given collection of gas molecules. We do this by holding the number of gas particles and the temperature constant. What we see is that there's an inverse relationship between the pressure and the volume. Or in other words, if we take a system with a certain number of particles in it, and we push down on that system to decrease the volume, then the pressure of those gas particles will go up. And there's a strong connection to the kinetic molecular theory here. As the temperature is constant, we know that the root mean square speed is going to be constant. Thus, as we decrease the volume, we expect there to be more collisions, and because there's more collisions, there's an increase in pressure. With the graph on the left, we're looking at pressure as a function of volume, whereas on the graph on the right, we're looking at pressure as a function of 1 over the volume. So notice the difference in relationship between an inverse relationship and then the linear relationship by taking the inverse of the volume. Avogadro's law evaluates the relationship between the number of gas particles and the volume that they occupy. So this can be done by taking a variety of different gases and placing them in a container at a certain pressure and a certain temperature. And if you take 1 mole of any of these gases, then what you'll notice is that they occupy the same volume. So while there'll be different masses of gas particles, the number of gas particles are what are changing the volume of our system. And again, this is related to the kinetic molecular theory. That is, because the temperature is constant and the speeds are constant, the constant pressure, and because we also have constant pressure, the volume changes must be a result of the number of particles and the space that they as a collection occupy. Remember that gas particles expand to fill their container, and kinetic molecular theory also states that they themselves don't occupy any significant amount of space, but rather they're bouncing around, hitting the walls of their container. So we see Avogadro's law is showing us that regardless of the identity of your gas, if you have the same number of particles, then you'll have the same volume for a given temperature and pressure. Charles' law looks at the relationship between volume and temperature. This is done by holding the number of moles of gas and the pressure constant. And what we see is that as the temperature decreases, the volume also decreases. And there is a relationship here between kinetic molecular theory in that as the temperature decreases, so does the speed of the collection of gas particles. Thus, there are fewer collisions. But since the pressure must remain constant, the volume must also decrease in order to maintain the same number of collisions per unit area. We also see from Charles' law how we obtain absolute zero. So if you were to take any gas and decrease its temperature and look at the volume as a function of that temperature, what we see is that if we extrapolate those lines, then once we get to a certain temperature, they all reach zero volume. So while this is a theoretical temperature that we can never actually reach, we refer to this as absolute zero. This is the temperature at which there would be no thermokinetic energy for these gas molecules, and therefore the volume of those molecules would be zero. So when we determine the temperature in Kelvin, this is where the number 273.15 comes from. Our last relationship is the Gay-Lussac law. And what we're doing here is looking at the pressure of the gas as a function of the temperature. What we see is that they have a direct relationship. Or in other words, as the temperature goes up, so does the pressure. And there's a connection between the kinetic molecular theory. That is, that as the temperature increases, the speed will increase, whereas the temperature decreases, the speed will decrease. Thus, we're going to have fewer collisions. But since the volume must be constant, then the pressure of the system is going to decrease when the temperature decreases. So that's the Gay-Lussac law and the other laws as well. That's it for this video. Thanks for watching and have a great day.